Hello guys, my name is Ahmad bin Abdulatif and this is my friends.
My name is Absyar bin Yusuf Zaimi.
And my name is Muhammad Aufa bin Mahmud.
Today we are going to introduce you about our tetrahedron study hub.
Let's go.
Hello everyone, my name is Ahmad Nasrullah and you may call me Ahmad. Today my friends and I would like to talk about our project that have been discussed for 2 months ago, and we are going to show you our tetrahedron study hub. In this project we are going to show you how do we use vector concept in constructing tetrahedron pyramid hub. So as you can see here, let's move on to the table of contents first. There is an introduction where we will discuss about production progress and mathematics analysis, and the second one is dot product. So in this subtopic I will clarify how to calculate angle at C and calculate angle at A. And the third one is cross product. In this project, the cross product is used to calculate the area of the triangular plane on the tetrahedron. And then we would like to talk about normal vector, which is we want to determine which direction the wall is facing. And then there is a reflection, and the last one is conclusion. So before we move on to our project, I would like to talk about what is tetrahedron. Tetrahedron or pyramid is a polyhedron because it is a three-dimensional solid formed by a polygonal face joint at edge and vertices. In the real world, pyramid has become a physical structure rather than an abstract shape. Real-world pyramids are not only studied for their shape, but also for their historical, cultural, and practical purposes. So, based on our project, this is a great project that I have ever discussed, because it provides space for students to discover new things and gain new experiments in gaining knowledge. So what about the production progress? So we have discussed that a pyramid is formed by a triangular base defined by three vertices and a single apex rising above it. So as you can see here, there is a question: why vectors matter? First of all, vector is modeling reality. Vectors encode both direction and magnitude, essential for defining structural age, loads, and orientations in 3D space. And second one is safety analysis. Engineers utilize vector operations, which is dot and cross product, to precisely evaluate angles, surface slopes, and force distribution balance. And the last one is geometric verification. We will specifically compute side slope via dot products to assess whether the design meets safety standards for climbing. After the discussions, we have decided to choose 3 points to form a triangular base, which is A, B, and C, which is based on the horizontal plane where z is equal to 0. So as you can see in the box, I have listed down the points here, A, B, and C, which is z is equal to 0. So we have A, which is at -4, 4, and 0. B 4, 4, and 0, and C 0, -4, and 0. So we have located point P act as the apex, positioned vertically above the origin, creating the height of the pyramid. So this configuration creates a tetrahedron, which is a fundamental structure form known for inherent geometric rigidity and resistance to deformations. Right, so in this part I will clarify how to find angle at C using the dot product. So note that dot product use two vector, which is we get here CO and CP. First we have to find CO first. We know that CO is equals to 0 negative OC, so we get here 0 for 0, and then we find another vector which is CP, and we get 0 for 6. So next we calculate the dot product, which is CO multiplied by CP. So how do we calculate the dot product? Here is the set. 0 multiplied by 0 plus 4 multiplied by 4 plus 0 multiplied by 6. So we get 60. And then we calculate the magnitudes, which is CO, the magnitude of CO multiplied by magnitude of CP. So how to calculate the magnitudes? So the magnitude of CO is the square root of 0 square plus 4 square plus 0 square, and then multiplied by square root of 0 square plus 4 square plus 6 square. So the final answer is 8 set 3 13. And then we can transform the formula to find the angle theta. So we get here cos theta is equals to the dot product divided by the product of magnitudes. So we just substitute the answer that we have discussed just now. So we get 0.5547. So we want to theta is equals to r cos 0.5547. So we get here 56.31 degree. So another section is we want to find angle at A, which is requires two vectors, which is AO and AP. So first we find the AO. Absolutely, and there is no doubt that AO is equal to negative OA. So we get here AO is equal to 4, negative 4 and 0. And then we find AP. So we get here AP is equal to AO plus OP. So the final answer is 4, negative 4 and 6. And then we calculate the dot product, which is AO multiplied by AP. So we get here 4 multiplied by 4 plus negative 4 multiplied by negative 4 plus 0 multiplied by 6. So we get the dot product is 32. And then we calculate the both magnitudes, which is magnitude of AO multiplied by magnitude of AP. So magnitude of AO, we get the square root of 4 square plus negative 4 square plus 0 square multiplied by the square root of 4 square plus negative 4 square plus 6 square. So we get the magnitude is 8/34. And then same goes to the next, same goes to the previous one, which is we transform the equation. So we get the equation is cos theta is equals to the dot product divided by the magnitudes. So we get we just substitute the value and then we get 0.6860, and then we want to find the theta. We get arc cos 0.6860. So the angle is 46.69 degree. So as you can see in the figure, we have plot where's the location of the angle. So we have C that we just found just now, which is 56.31, and then we notice that the angle A and B are equal, which is 46.69. That's mean the tetrahedron is symmetrical about the CO. So you can see here the CO is the midline of the AB. So this is a symmetrical tetrahedron. So this is very good construction, which is very good structure for the students to ensure their safety and stability of the pyramid. So the calculated angle confirm that the pyramid face are steep enough to provide structural rigidity while remaining accessible for the intended climbing design. So I have attached on this slide, which is the stability analysis, where we found that the identical angles at vertices A and B confirm perfect bilateral symmetry. This ensures that gravitational and climbing loads are distributed evenly across the structure spring. Using the dot product allows engineers to verify orientation and slope before fabrication. The math confirms the design meets geometric specifications independent of the physical skill. And then for the safety and accessibility, the variation in slope angles, which is steeper at C, more gradual at A or B, provides diverse climbing challenges while maintaining a coherent center of gravity above the base.
Okay, so now we're gonna talk about cross product. So what is cross product? The cross product is a mathematical approach that will be used to compute the exact surface area of a side of a pyramid in order to design a mirror. So cross products mainly used to calculate surface area of a geometry. So we're gonna find the cross product or the surface area for this tetrahedron. So we need to have two triangles. We need to compare between two triangles. Which triangle side is more big, so we can easily use to build our mirror. Okay, so we compare two sides, PCA and PCB. So we have to find the PCA and the PCB. Okay, to find a cross product, we first need to find the vector of the plane that we want to calculate. First, we're gonna calculate the triangle PCB. So we need to use two two vector, that is vector CB and vector CP. So to find the vector CB, we use vector CO plus vector OB. 0 times 4 is 4, 4 times 4 is 8, 0 plus 4 is 4, 4 plus 4 is 8, 0 plus 0 is 0. And for vector CP is CO plus OP. And it is 0 plus 0 is 0, 4 plus 0 is 4, 0 plus 6 is 6. So now with this vector, we can now find our cross product. So the cross product is we need to cross our product. Our product is CB and CP. So we just cross it like this. And for example, okay. So for example, we want to find the I, right? So we need to cross the J and K. So 8 times 6 and 4 times 0. 8 times 6 is 48. 4 times 0 is 0. And we repeat for J and K. So for J is 4 times 0, 4 times 6, and 0 times 0. 4 times 6 is 24, 0 times 0 is 0. 4 times 4 is 16, 0 times 8 is 0. And remember, here is minus, and here is always positive. And we got the cross product for PCB is 48i, negative 24j, and 16k. The cross product gives the area of parallelogram formed by those vectors. Since a triangle is half of that parallelogram, the area of triangle is half. Yeah. So using this coordinate, we can find the what is called parallelogram shape like this. But since triangle is half parallelogram, this is triangle, half the parallelogram, so we need to calculate it by half. So half the magnitude of this cross product, we got 1 divided by 2 times the magnitude is 56. 1 half of 56 is 28. Okay. So that's one. Next, we're gonna find the cross product for triangle PBA. So for this triangle, we have to find the vector for BA and BP. BA, like always, negative 4 plus negative 4 is negative 8. Negative 4 plus 4 is 0. 0 plus 0 is 0. For vector BP, is negative 4 plus 0 is negative 4. Negative 4 plus 0 is negative 4. 0 plus 6 is 6. So, again, we use a vector product to find I is 0 times 6. Negative 4 times 0. We got 0 minus 0. Negative 4 times 0. 8 times 6 and negative 8 times 6 first, and then negative 4 times 0. Negative 8 times 6 is negative 48. Negative 4 times 0 is 0. Negative 4 times negative and negative 8 times negative 4 is 32. Negative 4 times 0 is 0. Now we got 0i, 48j, and 32k. Like we just do. Now we need to half this magnitude. First, find the magnitude. BA magnitude of cross product BA and BP is 16 sub 13. Half of 16 sub 13 is 8 sub 13, or equivalent to 28.84. So since the area of triangle PBA, this triangle, is greater than PCB, is greater than PCA and PCB. So for PCB, we got PCB is 28 and PCA is 28.84. So means 28.84 is greater than 28. So logically, we're gonna use triangle PBA to do mural because it is larger. Next is normal vector. Okay, so in this section, we should understand which directions the wall face. The cross product is used to determine a normal vector, which is perpendicular to the triangle PAB. So this time, we're going to see where the triangle is facing so that we can see the mirror. So what does it mean by normal vector? So imagine this is a triangle, right? Normal vector is perpendicular to the triangle. So this is a normal vector or n. Okay, so we have to find n is BA cross product to PB. To find the normal vector, we can use cross product. So BA cross product to PP is BA. To find BA, we have to BO plus OA. We got negative 8, 0, 0. BP is BO plus OP. We got negative 4, negative 4, 6. Now, we calculate the cross product. Okay, so now to find the cross product is like like always 0 times 6 is 0, negative 4 times 0 is 0, negative 6 times 6 is negative 8 times 6 is negative 48, negative 4 times 0 is 0, negative 8 times negative 4 is 32, negative 4 times 0 is 0, and remember always negative and always positive. We got 0, 48, and 32. Okay. Generally, the mural is visible only if the central point is on the front facing side of the plane. The center of the part has a point at D, negatives 10, 10, and 0. The angle between the normal vector and the viewing vector demonstrate whether the triangle mural is oriented towards or away from the center of the part, allowing observer to see the mural clearly if they're standing at the center. Meaning, if we stand at the center of the part, we should see the mural perfectly. This diagram shows that the normal vector n lies on the triangular plane through a point h is 0, 28, 1.87 by forming a viewing set vector from the center. Spatial alignment can be clarified mathematically based on the calculation using dot product. The viewing vector can be expressed as HD equal to HO plus OD, and that is HD. The H is 0, 22.8, and 1.87. So to find HD is HO 0, negative 22.8, negative 1.87 plus negative 10, 10, 0. This is we want to find if we can see it. Okay. To compute the dot product, we got 285.76, and to find the magnitude, we got the magnitude for it is 718.80. So now we got the dot product and the cross and the magnitude. We can find the theta. So the theta is 16.657. So we're gonna continue to the next person.
Okay, so I will continue about the visibility proof of the mural from the center of the part. By calculating the dot product, which gave us 285.76, and resolving the viewing angle, we determined that the angle is 66.57 degrees. Because 66.57 degrees is an acute angle, meaning it's less than 90 degrees. This tells us that the viewing vector points is the same directional hemisphere. Ultimately, this mathematical proof guarantees that the mural is perfectly visible from the center of the part. Moving on to the core concept of our design, inclusive learning. Our main purpose was to create a tetrahedron study hub that caters to all types of learners. We specifically designed this to help those who benefit from a multi-sensory approach, incorporating visual, tactile, and kinesthetic elements. To achieve this, we integrated mathematical concepts with sensory and physical stimulation. The hub focuses on three specific phases, which are phase PAB for mathematics, phase PBC for 2D shapes, and phase PSC, which acts as a sensory climbing wall. Okay. Now, let's look closer at the inclusive design of these three walls. First, wall PAC is our sensory climbing wall. It is equipped with climbing holes in geometric shape, featuring distinct textures like rigid, bumpy, and smooth surfaces. This integrates gross motor skill development through climbing with interactive shape learning. Furthermore, these texture grips provide excellent sensory feedback, ensuring both physical safety and mental stimulation. And second, wall PAB is dedicated to tactile tessellation and counting. We built 3D numbers and mathematical operation symbols with raised tactile surfaces. This allows visually impaired or sensory learners to physically feel the numbers, while high contrast colors are used to enhance visual recognition and engagement, while wall PBC focuses on the foundation of shapes. It displays basic geometric shapes like circles, triangles, square, and hexagons in embossed and textures formats. This stimulates cognitive development through pattern recognition and shape matching, enabling students to learn about polygon properties such as edges and vertices through touch. As we reflect on this project, we want to emphasize a few key takeaways. First, we rely on fundamental principles, demonstrating that mechanics is essentially a deductive science based on core principles. Second, we heavily apply vector concepts. We justified the structural stability of the pyramid using vectors rather than relying solely on angle measurements. Finally, through structural analysis, we use the vector relationships between different points to definitively prove how the triangular faces create a strong, stable framework. Right. To conclude, this project was a fantastic exercise in collaborative learning. We co-constructed knowledge between teachers and students through inquiry, creativity, and mutual recognition. The project highlighted the importance of spatial visualization, which is critical for promoting mathematical learning. By focusing on 3D manipulation, we work on manipulating figures in three-dimensional space and recognizing patterns and projections. Lastly, it improved our concept articulation, allowing us to practice describing complex concepts effectively using both natural language and mathematical terminology. Our work was informed by a variety of academic sources covering vector mechanics, spatial thinking, and inclusive education, which you can see listed here in our references. Thank you so much for your time and attention today. I would be happy to answer any questions you might have. Thank you and bye-bye.
Okay, you have heard all about the information about the tetrahedron study hub. So I hope you enjoy with my project, with our project, and
You can ask questions if you have
Yes.
some questions.
Yes.
That's all from us. Bye-bye.
Bye.